Hi, today I am going to discuss our ICSE 22 paper, Multilingual Training for Software Engineering. I am Toufique. I am a fourth year PhD candidate from UC Davis. This work was done by me and my advisor, Professor Premkumar Devanbu. Modern deep learning models have millions and billions of parameters, and it is not easy to train such models with limited amount of training data. So in this paper, we propose a novel approach to augmenting the training dataset. Let's look into the motivations of our work first. The dataset creation or curation is a slow and effortful process. It always requires some form of human involvement. And we have also seen that for some languages like Ruby, the labeled dataset is less abundant. And for some languages, the data is more domain specific. So, augmenting the dataset is quite challenging. On the other hand, we found that the performance of the deep learning model in several software engineering tasks depend on identifiers. Luckily, identifiers are not language specific. It preserves across different languages. And that thing inspired us to believe that maybe multilingual training can enhance the performance of deep learning models in these software engineering tasks. We applied our idea on three different software engineering tasks. Let me introduce you to the task first. The first task where we applied multilingual training is code summarization or code comment synthesis. The second one, code retrieval or code search from natural language description. The third one, extreme summarization or method name prediction. For all these three tasks, we used a multilingual dataset, the Codex Glue, which is a modified version of Code SearchNet. The data comes from 6 different languages: Java, JavaScript, Ruby, PHP, Python, and Go. Multilingual training is not new in natural language processing domain. There are several works where the authors have found that multilingual training is beneficial for low resource languages. And the benefits are observed in two situations: when the languages are low resource and they are related to each other. We have a very similar situation with Codex Glue also. We have Ruby and JavaScript, which are low resource because we have very few examples to train the models with the data from these two languages. And we also believe that these languages are related to each other via identifiers. We will look into this hypothesis in detail later in this presentation. There is another advantage of using multilingually trained model. When we use a multilingually trained model, we are replacing multiple models with only one. So multilingually trained models are easy and more practical to deploy. Now I will introduce you to the first task where we applied multilingual training, the code summarization task. The objective of the code summarization task is to generate a natural language summary for the given code. So in this slide, you can see one function and one comment associated with that function. So the input to the model will be this function and the output will be this comment. Now in the code summarization task that I have introduced in the last slide, what information is basically used by the machine learning model to do the summarization? Does every token in the function matters, or the models are basically extracting the information from function and variable names? And we found that the function and variable names matter most in code summarization task. Let's get back to the example that I showed you before for code summarization task. There is one function called getTextContent and one comment associated with it. And the comment is return the text content of this node and its descendants. So if you carefully look into the comment, there are 4 major tokens: returns, text content, node, and descendants. And out of these 4, 3 of them are directly or indirectly present in the program. The last one, descendant, is not there, but there is another token, child, is present there. And the high capacity deep learning model may be able to derive descendant from the word child. However, the main objective of showing this slide or example is that maybe the model does not need other token for the function like public, string, the parenthesis, the curly braces, the plus one, the equal, the semicolons. The model is only need this like the identifiers for the summarization task. We'll look into this in more detail later in the presentation. So far we have discussed about 2 major ideas that are important for multilingual training. The first one, does the performance of the deep learning model depends on the identifiers? The second one, whether the identifiers are language dependent or not. So we formulate two research questions from these two ideas. The first one, what role do identifiers play in code summarization task? The second one, do programs that solve the same problem in different languages tend to use similar identifier names? That means identifiers mostly dependent on the algorithm, not the programming languages. So in the following slide, we will try to answer these two research questions. To answer the first research questions, like do identifiers play the most important role in code summarization task, we generated two new datasets from the original one. One is identifier de-emphasized version, where we abstracted out the identifier and keep the keyword operator and separator intact. And the another one is identifier emphasized version, where we keep the identifier intact but abstracted out the keyword operator and separator and replace them with three generic tokens. So we also took four programming languages for this experiment from Codex Glue. The two of them are low resource like Ruby and JavaScript, and two of them are high resource like Java and Python. Both Java and Python has more than 100k examples for the training purpose. So we trained the summarization model for all four these languages with three types of dataset and observe the results. So if we compare the complete the results we achieve from complete program and the identifier de-emphasized version, that means where we abstracted out the identifier, we can see that the performance drops a lot. Like for Ruby we had 12.53, it becomes 7.94. For Java it was 18.72 and it becomes 11.41. That means for all four languages the performance drops a lot and the effect size is also very high. But on the other hand, when we take the complete program and identifier emphasized version, that means we abstracted out the keyword operator and separator, you can see that for Java the performance remains the same. Like for both version we got 18.72. Even for Ruby, JavaScript and Python, the performance drops a bit, but the difference is not very significant for all the languages or all the cases. So this experiment shows that like the identifier is actually playing the most important role for the summarization task. When the identifiers are gone, the performance drops a lot. But when the identifiers are there, we drop the keyword operator and separator, the performance doesn't change that much. To show the promises of multilingual training, we have performed another experiment. We called it intra and interlanguage training and testing, where we train the model with the data from one language and test it with the data from another one. And we took all 6 languages from Codex Glue and tried all possible combinations. And we can see that for high resource languages like Java, Go, PHP and Python, we are getting the best results in the diagonal positions. In the diagonal positions, the training and test data are coming from the same languages. But surprisingly, this is not true for low resource languages like Ruby and JavaScript. We are not getting the best results in the diagonal positions. Rather, Ruby test set is doing well when the model is trained with the data from Java, PHP and Python. And this is true for JavaScript also. That indicates that code summarization sometimes appear to train quite well with the data set from other languages, even if the syntax is very different from each other. Now we will discuss about our second research questions, that identifier preserves across different languages. That means identifier mostly dependent on the algorithm, not the programming languages. And to motivate the viewers, we have presented one examples from the Codex Glue dataset. So here we have index of function implementations in 3 different languages, Java, JavaScript and PHP. All of them are from GitHub, and you can see that all 3 implementation have used very similar identifiers, haystack and needle. That indicates that the identifier is dependent on the algorithm, not so much on the programming language, and deep learning model can be benefited from multilingual training. In this slide, we will continue our discussion on our second research question. It is very difficult to prove this hypothesis because it requires multiple implementations of the same algorithm in different programming languages. It is very difficult to build such dataset. Thanks to Rosetta Code to provide us with such dataset. And using Rosetta Code, we will show that identifiers are not language dependent. It mostly depends on the algorithm. So to do so, we mine the dataset from Rosetta Code and study six programming languages. We measure the identifier similarities between the pair of programs solving the same problem and compare it with a randomly chosen pair of programs. That means, suppose we have two languages, Java and Python, and we choose one algorithm, shortest path. So we take the implementation of Java and Python and calculate their identifier similarities. Then we keep the shortest path implementation of Java and replace the Python one with some random program and then calculate the identifier similarities again. Then we compare those identifier similarities and we'll see whether the problems solving the same algorithm has higher identifier similarity. So while choosing the random program pair, we also take care of the length issue. So if our shortest path algorithm in Java has 500 tokens and the Python implementation has 300 tokens, we replace the Python one with another program that has something around 300 tokens to avoid any biases. Now we will discuss the results we achieved from our Rosetta Code experiment. As I already mentioned, we compare the matched and random pair overlaps using the non-parametric Wilcoxon sign rank test and see whether the programs solving the same algorithm have higher identifier similarities than the random one. So this is the results we achieved from this experiment. We have 6 programming languages that produce 15 programming language pairs. And for each programming language pair, we can see that the overlap coefficient is much higher for the programs solving the same algorithms than the random pair. And this test proves that identifiers are not dependent on the programming languages, rather it dependent on the algorithm itself. In this slide, we will discuss the evaluation plan in detail. As I already mentioned, we are aiming for 3 software engineering tasks for multilingual training: course summarization, course search, and method name prediction. The dataset and evaluation metric we are using in this paper are well accepted by the community. Regarding the models, we are using some form of foundation models, CodeBird and GraphCodeBird, for the experiment. Foundation models usually have 2 stages. In the pre-training stage, the models are trained on a large amount of unlabeled data in a self-supervised way to learn the statistics of the language. In the fine-tuning stage, the models are trained with labeled dataset. I would like to mention that multilingual training is already well accepted in the pre-training stage. Almost all the pre-trained models are trained on multilingual dataset. However, none of the prior work has tried multilingual fine-tuning. In this paper, we show that multilingual training is helpful in fine-tuning stage also, and it can enhance the performance of the deep learning models in several software engineering tasks. Before discussing the results, let me introduce you to the dataset. So this is the dataset we used for all 3 tasks, and as you can see that Ruby and JavaScript have much fewer examples compared to other 4. This is the reason why we refer Ruby and JavaScript as low resource languages and other 4 as high resource languages. And on the right hand side, you can see the candidate course. The candidate course only used for course search problem. Note that there are many projects in GitHub that are written in C, but we called it low resource because of the artifact of the CodeExclude project. I am presenting the detailed results using multilingual training on course summarization task. As I already mentioned, we tried 2 models for code summarization task, the CodeBird and GraphCodeBird. We achieved 17.83 and 18.08 respectively for these 2 models. So let's look into how much we achieve with their multilingual counterpart. So the multilingual counterpart of CodeBird, Polyglot CodeBird, achieved 19.06 BLU4 and Polyglot GraphCodeBird achieved 19.10, which is much higher than their monolingual counterpart. Though we have seen improvement for all the languages, but the improvement is much higher for the low resource languages like Ruby and JavaScript. In the last slide, we presented that our multilingual models are better than their monolingual counterparts. In this slide, we will compare our multilingual models with other work. If we look into the table, our polyglot models have achieved state-of-the-art performance on course summarization tasks. The model ProfitNet X scored 18.54 on CodeSleuth dataset, where our model scored more than 19. So this also indicates that multilingual training is helpful and it can help model achieve state-of-the-art performance in several software engineering tasks. We observed similar performance improvement with multilingual training on course search and method name prediction tasks. For course search, we achieved 2.74% performance improvement with multilingual codebird and 1.54% improvement with multilingual graph codebird. We achieved much higher performance improvement on method name prediction task. The improvement was 10.09%. Please look into our paper for more detailed results. Let me summarize the overall contribution of this paper. Using Rosetta code, we showed that identifier name choice is well conserved across languages. That means identifiers are not language specific. It depends mostly on the algorithm. We also observed that cross-lingual training helps. If the model is trained with the data from one language, it can help the data from another one. And this experiment inspired us to explore the potential of multilingual training in software engineering tasks. We have also tried to answer one important question regarding identifier, and we found that identifier names may matter more in the training data. So if you remember our course summarization task, we found that if we drop the identifiers, the performance degrades a lot. And if we keep the identifier, the performance doesn't degrade that much. That proves that the identifier is playing the most important role in course summarization task. And at the end of this paper, we tried multilingual training on several software engineering tasks like course summarization, course search, and method name prediction. And for all three tasks, this multilingual training have shown significant improvement. So thank you for listening to my presentation.